Let's start. So I have made a few changes in the lecture notes, the yesterday's lecture notes. So if you go to the Canvas, you probably can download the new version. I had a typo here, just a conversion of the constants from the diameter to the radius. They can just change this. This is 8 instead of 16. Then I also add the derivation of these expressions using the F equals ma, Newton's second law, to derive this equation here. So you can just follow these steps, because this is not the derivation from the differential equation, which you can apply that here. So that's your job. So at least I did this job, so we can just take a look at it. So the answers should be all same. All right. Now, so we use the F equals ma, and we use a differential equation to get the velocity profiles and the pressure differences and so on. And the problem is, especially for the turbulent flow, it's really hard to solve the Navier-Stokes equation directly. Even if we had a lot of boundary conditions and assumptions, but it's pretty much numerically solved, then we have to put a lot of efforts on it. So what are you going to do? So the most popular method is using the dimensional analysis, like we did. Just get the dimensionless groups for the specific problems, then find the unknown function between the dimensionless groups. Then we can just find that the function or the constants between the dimensionless groups empirically, numerically, so on. So what we did in the previous lecture, especially the lab lecture, the Thursday one, I went through these steps already. So you can just take a look at the video. Then the lecture notes, you see I added like a few more variables in the dimensional analysis. So here we used to have delta PL, right? That was the pressure drop per unit length, but now I just change it to the pressure drop. Then velocity, diameter, length, surface roughness, and viscosity, density. So we think those variables are the important, pertinent in this experiment. Then we just try to include all of them. When you just do the dimensional analysis, you will find these expressions. Of course, you may not have this constant 1/2, but in the video I explained that we want to kind of tweak the shape of the dimensionless group in terms of the common dimensionless group we know of, which is Reynolds number is the most popular one. Another one is a dynamic pressure. We normally use a 1/2 rho v square, so we just change the shape of the dimensionless group here in terms of the pressure drop per dynamic pressure. So we just add a 1/2 here. That's all we did. It's doable because we still don't know what the function here. Therefore, we can just add any constant here. It's going to change the multiply with the constant, right? Then what we found was we have a very reasonable assumptions that the pipe length is directly proportional to the pressure drop. So we can just take this L/D out of the function. We can just simply make a relationship between the pressure drop group to the pipe length group proportionally. So it has a linear relationship. That's what we did. Then we can just isolate this two-dimensional group within the function. Then we just set it as a unknown dimensional group here. Then we just threw the new concept here, new idea terminology said the friction factor, more accurately we call the Darcy friction factor F. Then we just define this whole term, unknown function with the surface roughness and the Reynolds number, the function of the surface roughness and the Reynolds number as a friction factor. Okay, from here, we just put some more assumptions now. So if it's a laminar flow, all right, laminar flow, it is built with no slip condition from the wall. Then we don't have any kind of effects by the friction, the surface friction, the surface roughness. So we can just take this dimensional group out. It's same process that we do not include the surface roughness initially in the dimensional analysis. Then take it out, then find it. You will just have a the dimensionless group here. All right. Then we can just simply take this out. Then this term is now the function of Reynolds number. All right. So what I'm going to do is, I know this relationship should be valid, this whole thing. Then we have an exact solution from the Navier-Stokes equation, right? Or from the first step, using the F equals ma. Either way, we can have the exact solution for the flow rate and the velocity profile and the average velocity, maximum velocity, and so on. So I just brought the exact solution of the flow rate, Q. It's a pi d4 to the fourth power, pressure drop, 128, viscosity, L. That's all given here in the previous lecture. Then we just rearrange the terms here in terms of like viscosity, length of the pipe, velocity, diameter for the pressure drop. All right, that's what you can do. Still same equation. Then just divide by the dynamic pressure, 1/2 rho v squared. All right, we can do that. Then what you can see is you can group some of the constant here and the variables in terms of Reynolds number, the reciprocal of the Reynolds number, and the pipe length over diameter. All right, what it did was we tried to fit this equation, exact solution, into the form of the result out of the dimensional analysis. All right, so we have a L over D that's still there, and we have a Reynolds number and the constant 64. So when you just put this together, then say this is the same concept that we use for the friction factor. So we can easily find the friction factor F equals 64 divided by the Reynolds number. All right. If the flow is a laminar, you can just use the friction factor equals 64 divided by the Reynolds number. All right. That's the range. Yeah, of course, Reynolds number should be less than 2,100. As long as the Reynolds number is less than 2,100, you can use this number. So what's the advantage of this equation? If you have the pressure drop, you can find the velocity. If you measure the velocity, then you can find the pressure drop, right? Because you know the relationship completely by the friction factor. All right, what if the flow is a turbulent? It's a little bit different story now. All right, if it's a turbulent flow, there's no way you can just apply the shear stress relationship, which is tau equals viscosity du over dr or du over dy. So we just bring the pretty much a rudimental relationship between the wall shear stress to the pressure drop. You can go to probably page 3 in the previous lecture. 1, 2, 3. Yeah, here. Then when you do the force balance onto the fluid element here, then we found that there's a relationship between the wall shear stress to the pressure drop. So we're gonna just bring this expression instead of the laminar flow. Then it's exactly the same. We just rearrange the terms in terms of for the pressure drop as the function of length of the pipe, wall shear stress. Now instead of the viscosity, we have to maintain the wall shear stress here, then over D. All right, what it did was trying to fit this equation into the dimensional analysis, which means we can just divide by the whole thing by the dynamic pressure, right? Then what we have is we can define the friction factor for the turbulent flow. Then that can just expressed in this term. wall shear stress over rho v squared. All right, what you can find here? Yep, nothing here. So either you have to measure the wall shear stress, which is very difficult to measure. Then you can find the pressure drop, or you can find the pressure drop, then calculate the wall shear stress, but you also need to know the velocity. All right. One way is really hard, right? Measuring the wall shear stress is not that easy job. So normally what you can do is we can measure the pressure drop, right? You can just put the pressure gauge onto the pipe, then measure it. Then you know what the wall shear stress is. Then when you know the wall shear stress is, then you know what the friction factor is. Then because you know the velocity. How? You just measure the flow rate of the pipe, then divide by the average, the area, cross-sectional area of the pipe. Then you can find it, right? Then that way you can just measure, like calculate the friction factor, and later for the either the pressure drop from the to the pressure drop to the wall shear stress, or the friction factor, you can calculate it. Later you're gonna find the loss coefficient from the lab, and those kind of stuff. But it's pretty much the one-way calculation. All right, using the energy equation, we learned all the energy equations from the chapter 5. So if I just bring the one of the energy equation, that is for the incompressible steady flow between the two locations within the pipe, and there's no shaft work, so we don't put any work into the fluid. In that case, this is the equation from the chapter 5. Then here the alpha is kind of coefficient for the non-uniform velocity profile. As you know, if we just make assumption that the velocity profile is a uniform across the cross-section area, we can just set it that alpha equals 1. Then we can just rearrange the terms for the head loss, which is the same as the pressure loss, and this is not head loss because you can just divide by the rho g for the entire equation. So that's why we use the head loss in the unit of the meter or the feet, something like that. Then if we know the velocity is same in the inlet and outlet, let's say the diameter of the pipe is consistent, we can just remove these terms. It's going to be same. Then finally, we can just find the head loss is same as the pressure drop. So pressure is always higher in the inlet side. So it's going to be P1 minus P2. Then it's going to be the pressure drop between the two locations and plus the height change of the pipe. Okay, when you go back to the previous lecture note, especially the one I added at the end of the lecture note, when I drive it, that's the force balance equation here. So when you do it, then you can find the relationship between the pressure drop equals 2 shear stress, length of the pipe over R, then the P rho g L sine theta. So this sine theta is because of the tilted angle of the pipe from the horizontal angle, which is a 0. Then what you can do is you can rearrange this one. So when you have a pipe here tilted, let's say this is G. So this is going to be the theta again. So L sine theta is basically Z1, Z2, Z2 minus Z1, right? So here, we just try to match this equation here to there. Then we include the negative sign in front of the L sine theta. Then you can simply change to the Z1 minus Z2. Then set the head loss here is going to be the pressure drop within the pipe and the height change of the pipe between the two locations. So we can conclude that the head loss is going to be the same as the 2 shear stress L over a specific rate, which is rho g r. Okay. So still we have keep the shear stress inside, so it's not that useful at this point. All right, let's talk about the turbulent flow now. So I'm not going into like details of the turbulent flow. Let me just know what that is. Then we can use the empirical data sets and the graphs to figure out how we can just determine the velocities within the pipe and especially the loss coefficient, head loss within the turbulent flow. I think that will be good enough, especially for the lab and this chapter. If you are more interested in turbulent flow, of course, we're going to talk about it, but mathematically, it's going to be a little bit challenging. Also, it's going to be not give you the exact solution anyway. You have to run the numerical analysis or design the experiments to measure it for every single problem. Right? That's actually the issue. All right, so turbulent flow. So turbulent flow, it's not just coming up suddenly. It is built up from the laminar flow. So when you just increase the velocity, let's say this is really for the presentation, visualization of the graph. So this is quasi-static flow change for the graph. So it's not going into that details like changes like this details. But for example, let's just increase the velocity slowly, very slowly. Then it's not gonna make the small eddy currents mix another thing on and on. Just let's say it's just pure effects by the velocity increase. All right, from the slow velocity, then it's going to the laminar flow. It's going to increase the velocity linearly. Then after a certain point, of course, it's going to be laminar the Reynolds number around like 2000. You'll see a little bit of the eddies there. Let's say vortices or a little bit of rollings, what they say, and something like a bubble-like shape. Then you're gonna see a little bit of the kind of some vibration or things if you measure it, the random effects. Then it's going to getting worse and worse when you increase the velocity. Then after 4,000 of the Reynolds number, that is pretty much, settled down, which means there's still crazy randomness vortices inside in the flow, but they're kind of break each other into the small size of the vortices. So in average, you'll see the lot of noises, but that's going to be form a pretty much uniform average value of the velocity. So that's what you can see. So if you measure the turbulent flow, it's going to give you a lot of noise, but that's not actually the noise. It is the actual velocity of the turbulent flow within the pipe. So how can you characterize the velocity then? Yep, the instant velocity is going to be crazy like that. Go up and down, sometimes faster, sometimes slower. So what you can do is just measure it for a certain period of time. So let's say this is T, capital T is the time interval. So you measure like 1 or 2 seconds or 3 or 4 seconds, or if the turbulence is strong enough, you can, if it's strong, then actually you can just measure it a little bit in a short time, but you measure it for a certain time. Then get the average of the value, then it's going to be the average velocity. All right, that sounds good. So If I have the instantaneous velocity of the turbulent flow, then it's going to be u bar plus minus u prime. So u prime means the fluctuation. So fluctuation of the single fluctuation from the average value. Of course, you can go further more, but that can be, you need to specify the average fluctuation into this equation, right? Because it just sometimes it's small, sometimes it's large, sometimes it's moving forward, sometimes it's moving backward. So what if I just get the measurement of the average of this measurement? So if I just do the average, and for the velocity, so you can just simply do from t naught plus capital T, and u, of course, this is function of time, dt. And you can divide by a whole thing. Let me just have a little bit more space here. Capital T. Then you can find the average velocity, right? That's what you usually do. How about the fluctuation now? All right, it's moving back and forth. So let's just take the average value, then 1 over. So let me just do it this way. I'm gonna just set one equation. U is u bar minus u prime. Then say you can say u prime is going to be u minus u bar, right? Then let's find the average of them. So u prime average is going to be 1 over t naught plus time, then u minus u bar dt. Okay, you can separate it. So first term is going to be the average of the velocity. So that means it's going to be just simply u bar. Then the average of the velocity is going to be give you the same average value. So it's going to be u bar and equals to 0. So you're going to end up having the 0 for the fluctuation. So that's why we use a little bit different approach for the turbulent fluctuation, using the square of the fluctuation. Of velocity fluctuation. Here. So what we have is we have a square of the fluctuation, then get the average. So that way, this fluctuation always gives you the positive value, right? Then this whole thing has to be always positive. If it's 0, it means you have a laminar flow. So here we have another definition, says turbulent intensity u prime square. This is u prime average square over u bar. So it's the ratio between the average square of the velocity fluctuation divided by the mean velocity. So it's going to give you the sense of the turbulent intensity. Okay. Then for the shear stress in the turbulent flow, So first, in the laminar flow, it was this one is a mu du. Let's use the dy or u du dr. This was the shear stress in the laminar flow. Then what you have in the turbulent flow, this is laminar. You have to define a little bit differently. So what you have is so you have a same portion of the laminar flow here. Then you have different the product of the this is U, by the way. Average of the fluctuation. So you have a negative rho U prime V prime. So this one give you the shear stress by the turbulent effect. So simply you can just divide these two components for the shear stress, then say this is laminar flow, laminar shear stress plus turbulent shear stress. Okay, so here the turbulent shear stress is defined by minus rho U prime V prime, or and if it's a 3D problem, you're going to have more terms. So V prime, W prime is also the one. Then we call this the laminar, the Reynolds stress. So this one comes up in the turbulent flow. So we have a more additional shear stress. So you might think there's a minus there. All right, it's going to be less than the laminar flow. No, it is not. So usually the U prime and V prime is in the opposite direction. So if you have a U prime, you might have a minus V prime. All right, what that says is it's same as the Poisson ratio or something like that. If you have a flows mainly goes into the one direction, then if I have a one fluctuation, things like eddy currents like that, then you always have the fluctuation of the U is slowed down. So probably have, let's just move a little bit more. U prime is going to be the negative and the V prime is positive. So you always, mostly, you have an opposite direction for these components. So that's why we have a negative sign here. Then it's going to end up, this whole thing is going to be mostly positive. All right, so you have a more shear stress in turbulent flow. Then in the figure here, you can see in the turbulent flow, let's take a look at the velocity profile first. You already seen this type of velocity profiles, axisymmetric one. So if I have a pipe like that, it's going to be like this. Of course, we didn't have a smaller size of the pitot-static tube. We can just measure this shape near the wall. We just probably just measure things like this, right? In the pitot-static tube. So you couldn't find it, but we have a little bit of a boundary layer there. All right, so that case, if you look at the shear stress of the flow, then there's a big differences between the boundary layer here to the center region here, what we call. Then we have a laminar flow contribution to the shear stress. And there's another contribution to the shear stress by the turbulent flow here. So this whole thing is going to be the total shear stress in the turbulent flow here, okay? All right, then how can you quantify or how can you characterize the velocities and the boundary layers or the flow rate in the turbulence? All right, it has to be done experimentally. So they threw a lot of experiments over and over. So it's really hard to define like a one common rule for the all flows. So they have a specific empirical data sets for the specific problem, especially for the pipe flow, because it's a really common system in the real world. They have plots and the data sets based on the experiments. So one they found is we have to characterize like three different layers within the turbulent flow. The first one is a viscous sublayer. So you might think about the regions very near the wall here that has a lot of slow velocity can be found certain distance from the wall. Then we characterize this layer as a viscous sublayer. That's near the wall. Then near the wall, we have a strong viscous shear stress works from the wall. So that is the dominant here, near the wall. And we have an overlap region. It's better to explain by the mixing between the viscous sublayer and the outer turbulent layer. So another layer is going to be the outer turbulent layer. Then here now we have a Reynolds stress, which we called like a minus rho V prime, and or the V prime, the W prime is now dominant. So it's going to be just there's a lot of vortices showing up. Of course, it's chopped down in the small scale in this case. Then overlap region can be defined by combination of the viscous sublayer and the turbulent layer. So the thing is, what they did is doing the dimensional analysis, then find the dimensionless groups for this experiments. Then what they did is not just using the variables, but model the behavior of the terminal flow. So there's several equations out there. Mostly they use like one or two, to characterize the terminal flow. But if you go to, like you might already see the CFD Fluent package when you set the laminar flow out of the viscous layer, then you have tons of list of the other flows, right? That was the one is the laminar flow, and the rest of them is all the turbulent flow. So they have a bunch of different models of the turbulent flow. Then they have a lot of different types of turbulent flow models in the specific case. So in this case, we are just focused on the pipe flow. So we have a few. So one is for the viscous sublayer. We have one here. Let's write down the equation first. So what we have here is U star, YU star, nu. So we call this as a law of the wall. So this equation can explain the velocity profiles, especially near the wall. So if you go away from the wall, then this equation doesn't fit to the data, especially empirical data. But here, let's take a look. So here, there's a U star, then nu is what you know. The U bar is, of course, you know what it is. It's the velocity of the flow. And the Y is the distance from the wall. So let's just define it. Y, distance from the, let's just R minus R, yep. So this is the distance from the wall. Then the U star is they call the friction velocity, but it's not actually the velocity. So let's write down the equation. It's defined by the square root of the wall shear stress divided by the velocity. So it has the unit of the velocity, so they call it as a velocity, but it is not actual velocity. It is called the frictional velocity. So this doesn't give you any physical meaning, actually. So this is just one of the modeled the variable for this equation. So if you just get these values out of the equation or from the plot, it's not give you the physical meaning, but you can use this value to find the velocity or the pressure drop you want to look at. All right? So let's take a look. So here, if you look at the figure here given, this is experimental data. You have all the points there. So what they did is model this equation to fit this data points. Okay, for the viscous sublayer, it's gonna really well fit between here to there. Let's change the color here. Then we can use this equation. All right, what's the x-axis? This is a y, u star, nu. And the left side, you have a v over v star. So what you can do is, if you're given the wall shear stress and the density or the velocity, you can put the numbers here, then find the value here, then go back to the graph and find the right number of the u bar over u star, something like that. Then you can track down the, find the velocity of the turbulent flow at a certain location. That's coming from the y here. If I see like a 0.001 millimeter out from the wall, what's the velocity of the flow? Then if I know the wall shear stress and the density, then we can just use this graph to find out. Well, another example is we have an example problem in the textbook that says to find the thickness of the viscous sublayer. Then, of course, the thickness of the sublayer is going to be the one here. Let's just exaggerate the velocity profile. And that's going to be this one, right? This is the r minus r. This is the thickness of the layer. Then what you can do is, all right, this is the boundary of the sublayer. So it's about like a 5. All right, for the sublayer, you can say the y u star over nu is a 5, approximately. Then this y is the thickness of the boundary layer, so you can just change it to the delta, and then you can say 5 nu over u star. Okay, you can find that the thickness of the boundary layer like this. All right, that's purely based on the experimental data. And what else? We define this. We have an equation for the sublayer. Then we also need the equation for the center region. This is for the first one. And then let's say this is a second to third. What you have is they call the power law velocity profile. Let's just write down the equation here. Just for the second one for now. You can have this equation in the textbook. The newer. So newer V. Let me check the equation if I write wrong. Okay, this is new. Cool. So they call the power law no dash velocity profile. And this can fit the data, experimental data, for like after the sublayer here, pretty much to the center of the pipe flow. So you can just use it to characterize the velocity profile in the center region of the pipe flow. So the overlap, you're going to have the little bit of mixing of these two equations in between. So if you can look at this, you have the one of the equation that called the law of the wall characterize the behavior like that. So you just cut it out after like a certain point, like in the middle of the overlap region. Then the rest of them is going to fit to the pretty much follow the power law velocity profile. So you have to use the two equations to kind of distinguish the flow region in this case. All right. This equation, it's the same. You have a nu and a u star is the same as the one we know, the friction velocity. So if you know the, let's say, wall shear stress and the density of the flow, which is the nu is here, then you can just plug the numbers and get this dimensionless group and get the number of the u over u star. Then also you can calculate what the velocity of the local points there. It's going to work like that way. How about the center velocity? So it's number 3. Let's just write down number 3. So there's several ways. You have a different equation in the textbook too. You have at least a 2 in the equation, and also you can use this second equation to set the, but the center location is the r minus, the capital R minus R is going to be just a 0, right? Then you can use that too. Then you can find the equations of the velocity profile, but mostly what they use, especially the textbook chose here, is the U bar. And this is overlap. So this one is actually the name of power law here. This does not have any name in the textbook, so sorry about that. So you can call this equation the power law velocity profile. And especially this one gives the velocity at the center line of the pipe. Then it's the function of the R, and then the function of the N. So it's gonna given as a function of the location of the R. So it's gonna intuitively give you the number right away though. So in this case, the N is the function of Reynolds number. So what can you do is go to graph to look up the data. So here, the procedure of the problem solving is going to be when you find the Reynolds number, then you go to the graph here, then read the graph, something like, let's say I have a 100,000 Reynolds number. Then I know, okay, the N is the 7. Then you can just put the N equals 7 into the equation that says, all right, if I have the average velocity of the flow, then I can solve this equation in terms of the velocity at the center line. Of course, this is a function of R. You may have to integrate this one to find the velocity, average velocity value, actually using the flow rate. So you're gonna just look at these application in the example problems. And if you look at the different n values for the turbulent flow, if the n is laminar flow, then this is actually really the pretty much the similar shape that we have in the previous chapters, right? We define the maximum velocity at the center line and plug into the velocity profile equation. Then we have this pretty much similar equations in the later part of the equation, right? Formula. You can look up the formula that we have from the Navier-Stokes equation. It's pretty much similar what you have here. Then if I have more n's there, it means the Reynolds number is higher, as we have in this graph. If you have a higher Reynolds number, the n values goes up. That means we have a higher velocity of at the center line, but the relationship is not a kind of linear. So that kind of shows you how much velocity can be changed based on the n value here. Okay, we have an example problem. Let's just solve the part of it. We have one here. Yep. I think we have time for the first part, at least. So this is example problem in the textbook. I'm not gonna give you like problems like this in the exam, but at least we have to know how we can use the graph and empirical data sets to fit the data, and using the fitting equation to find the one we in the lab, something like that. Of course, the lab is not about this one though. So we have a water system. And the density is given. And the kinematic viscosity or the viscosity can be given. And it's a horizontal pipe, and diameter is 0.1 meter. And the flow rate is given. The pressure gradient is given. So pressure gradient, you can think about the delta PL, which is delta P over L. That is the pressure drop per unit length. That's why we have a units of a kilopascal per meter. Okay, so just the problem solving is not a big of deal at this point. So you are just trying to find those values are available in real applications. All right, density. If I set the working fluid is water, you know the velocity, the density. Okay, you know the viscosity. Yeah, it's all pretty much given based on the temperature and the pressure. Diameter, you can measure it. Flow rate, can you measure the flow rate? Yeah, you can just collecting the waters out of the pipe, then just measure it and check the time. Then that's what you're gonna do in the lab 3, by the way. Then you can measure the flow rate. Then pressure drop. All right, I can put the 2 pressure gauges at the 2 locations. I can measure the pressure drop and divide by the length between the 2 points, right? So those values are pretty much readily measurable. You can easily measure these values in the experiment. So what you can do is now you can analyze the actual flow behavior within the pipe. So for example, like the first one, let's just solve one of them. Approximate thickness of the viscous sublayer. Okay, viscous sublayer. According to the graph, we can define that is up to the U V star over nu is up to 5. So what I can do is, like we did before, YU star over nu set as a 5. You can change the symbol here for the thickness of the layer, then simply just change it. Then U star is the root of the rho tau over rho. So here you can just rearrange it. 5 nu root rho over tau max W. So when you just plug the numbers, it's simple, right? You can just put the numbers. Then you'll find that the 1.97 multiplied to 10 to the minus 5 meter. So it's going to be 19.7 micrometer. All right. So according to the graph, you can actually have those macro size of the measurement, flow rate, density, viscosity of the water, and the diameter of the pipe. Then you can measure the thickness of the sublayer, which is fairly small, right? So only 20 micrometer. So if it's the case of our air duct lab, it's going to be really, really, really thin layer. So it's pretty much not measurable using the like centimeter size pirostatic tube, right? That's what you can expect it. All right, if you measure it, it's probably wrong. Okay, let's just move on to the rest of the sections here. Then I hope I can finish chapter 8 next week. Then the exam is tomorrow. Just don't be late. It's gonna just open up a little bit earlier, like 5 minutes early, and it's gonna close it after 15 minutes plus 5 minutes. I probably did it. So if you're just late like a five minutes, you're gonna still have like a 5 minutes more at the end. But you know, you probably have another class after this, so please don't be late. If you have any questions, please let me know before the exam. I'm not gonna help you out just like several hours before the exam. There's no way I can just help you. So just let me know today at least. All right, have a great rest of the day, and I'll see you tomorrow. Bye.